Hello everyone, I'm Professor Xiaonan Gao. Welcome to a general chemistry class. This session will continue with the chapter Chemical Bondings, the additional aspects. In last session, we discussed localized pi bond, such as those in ethylene. Some molecules, such as benzene, carbon-6, hydrogen-6, and substance related to its aromatic compounds have a network of the pi bonds. In this session, we'll use the bonding series we have studied thus so far to consider the bondings in benzene, the delocalized electrons. In 1865, Friedrich Kakulla advanced the first proposal for the structure of benzene. He dreamed about 6 monkeys connecting their hands and tails together to show the benzene-like structure. He suggests the molecule consists of a flat hexagonal ring of 6 carbon atoms drawn by alternating single and double covalent bonds, such as carbon atom is drawn to 2 other carbon atoms and to 1 hydrogen atom. To explain the fact that the carbon-to-carbon bonds are all alike, Kakulla suggested that the single and double bonds continuously oscillate from one position to another. Today, we say that the 2 possible Kakulla structures are actually contributing structures to a resonance hybrid. We can gain a more thorough understanding of the bonding in the benzene molecule by combining the valence bond and molecule orbital methods. A sigma bond framework for the observed planar structure can be constructed with 120-degree bond angles by using a sp2 hybridization at each carbon atom. End-to-end overlap of the sp2 orbitals produces sigma bonds. The 6 remaining 2p orbitals are used to construct the delocalized pi bonds. We do not need to think in terms of an oscillation between 2 structures of a resonance hybrid for benzene. The bonds are not localized between specific carbon atoms, but are spread out around the 6 member rings. To represent this delocalized bonding, the symbol for the benzene is often written as a hexagonal with an inscribed circle there. We can best understand delocalized pi bonds through molecule orbitals theory. 6 2p atomic orbitals of the carbon atom combine to form 6 molecular orbitals of the pi type. 3 of these pi type molecule orbitals are bonding, and 3 are antibonding. What do these pi molecule orbitals look like? Recall that as the energy of the orbitals increase, the number of the nodes increases as well. So we expected that the lowest pi molecule orbital will not possess a node. All 6 2p orbitals are in phase as indicated by the fact that all the blue nodes are on the side of the sigma framework. The next 2 pi bonding molecular orbitals each have 1 node and consequently have the same energy. That is, they are degenerated. The next pair of orbitals, which are antibonding pi orbitals here, have 2 nodes, and the final orbital has 3 nodes. The computed pi molecular orbitals of benzene are also shown here. The 3 bonding pi molecular orbitals in benzene describes the distribution of pi electron charge in the molecule. We can think of this in terms of 2 donut-shaped regions, one above and one below the plane of the carbon and hydrogen atoms. Because they are spread out among all 6 carbon atoms instead of being concentrated between pairs of carbon atoms, these molecular orbitals are called delocalized molecular orbitals. By using delocalized bonding scheme, we can avoid writing 2 or more contributing structures to a resonance hybrid, as is so often required in the Lewis theory. Consider the ozone molecule, O3, that we used to introduce the concept of the resonance in last chapter. This is the resonance structure of ozone. How do we find the real arrangement of the electron contribution in the ozone structure? We can follow these steps. Step 1. With Vesper theory, we predict a trigonal-planar electron group geometry. The hybridization scheme chosen for the central oxygen atom is sp2, and although we normally don't need to invoke hybridization for the terminal atoms, this case is simplified if we assume sp2 hybridization for the terminal oxygen atoms as well. Thus, each oxygen atom uses the orbital set as sp2 plus p. Step 2. Of the 18 valence electrons in ozone, assign 14 to the sp hybrid orbitals of the sigma bond framework. 4 of these are bonding electrons, and 10 of them are lone pair electrons. Step 3. The 3 unhybridized sp orbitals combine to form 3 molecular orbitals of the pi type. One of these orbitals is a bonding molecular orbital, and the second is antibonding. The third is a type is non-bonding molecular orbitals. A non-bonding molecular orbital has the same energy as the atomic orbital from which it is formed, and it neither adds nor detracts from the bond formation. Step 4. The remaining 4 valence electrons are assigned to the pi molecular orbitals. 2 go into bonding orbitals, and 2 into non-bonding orbitals. The antibonding orbitals remains empty. Last step. The bond order associated with a pi molecule orbital is 2 minus 0 over 2, which equals to 1. This pi bond is distributed between the 2 oxygen-oxygen bonds and amounts to 1/2 of a pi bond for each. The points listed here leads to a total bond order of 1.5 for the oxygen-oxygen bond in ozone. This is equivalent to averaging the 2 Lewis structures. Similar rules can be applied to the nitrate ion. There are 3 resonance structures for the nitrate and 2 orbitals of the non-bonding pi orbitals. Therefore, the final delocalized pi molecular orbitals for nitrate is this type. Alright everyone, in this class we learned the delocalized electrons. I hope you have enjoyed the class, and I'll see you next time.